ASDSO has a series of 2-hour webinars available on their website. These cover a great variety of topics, and I encourage you to check them out. For this video, we're going to be sealing different pieces from some of those webinars.
And when dam is inspected, sometimes we refer to the left and right. It could be the left wall, training wall of the spillway, the right training wall, the right abutment, the left abutment. And for consistency, whenever you're doing that, the left and right is if you're facing downstream. So if you're on the top of the dam and you're looking downstream, here we would have the right abutment, and then we would have the left abutment of the dam. We have the reservoir, and then we have the top of the dam. In this case, it's an embankment. It's an embankment crest. Now, I'm showing you a dam, and I'm saying it's typical, but there really is no such thing as a typical dam. I like what one of my colleagues says. He says, dams are like snowflakes. There's no two alike. Every one of them is unique. But most dams have typical features, and that's what we're going through right now. So the top of the dam is an embankment crest, and then the upstream slope of the dam, and the downstream slope. And then we have the part where the dam meets the natural terrain. At that intersection, that's called the groin. And you can have the left groin, the left upstream groin, the right upstream groin, the left downstream groin, and the right upstream groin. Then we have a principal spillway. In this case, it's a drop structure type spillway that's out in the reservoir. And there are all different kinds of spillways. But the purpose of the principal spillway is to maintain the reservoir level. So most of the time, water is flowing in the principal spillway. And then we have a conduit that passes through the embankment, and that's the principal spillway conduit. And then a low-level outlet, the discharge point at the toe of the dam. And then we have an outlet channel that conveys the water back into the natural stream. And then we have an auxiliary spillway. Sometimes the principal spillway and auxiliary spillway is combined, and sometimes they're separated. When they're separated, it's generally understood that the auxiliary spillway is there only to pass very rare extreme floods. In most cases, the auxiliary spillway will be activated for the 100-year flood or greater, and that's to prevent the dam from being overtopped. Now, dams are very interesting. They can have a lot of other features like this one does. They can have instrumentation to monitor the conditions within the dam. They can have gates, bridges. You can see in this one there's a bridge over the spillway. There are access roads, conduits and valves, and sometimes there may be a fish ladder at the dam. Now, let's talk about dam types. Here's a list of the major dam types that you might see. And the one thing you'll see that's in common here is that the dam type in this list really depends upon the kind of material or the type of material that it's made of. You can have an earth embankment dam, a rock-fill dam, a concrete dam, a masonry dam, a timber crib dam, a rubber dam or an inflatable dam, a steel dam. So the material is really the type of dam, the material that it's made out of. Now, we just don't have time to go through every type. But this graph just can show you the wide range of different dam types, like a timber crib dam here. Here we have an inflatable dam, a double arch, concrete dam, a buttress dam, a slab and buttress dam here. Here we have a steel dam or steel gates, a concrete gravity dam, and in the center we have our earth embankment dam. Now, the most common types of dams are earth embankment dams and concrete dams, and they make up almost 97% of the dam types in the United States. And here's a graph showing you the different dam types, listing them on the bottom axis, and then the number on the y-axis, and it becomes very clear that by far the majority of dams are earth embankment dams. So we're going to spend most of our time looking at earth embankment dams and the features and inspecting them. Now, just to give you a little historical background, the first embankment dams were homogeneous dams. In other words, the material that the embankment was made out of was uniform, and it consisted of available earth material from the site, and they would just be piled up to hold back the water. So that would be a homogeneous earth embankment dams. Oftentimes, it was built directly on the overburden. And the overburden is that loose material above the rock, the bedrock. So if you were to dig down far enough, eventually you hit solid bedrock. But all that sand, alluvium, soil, whatever loose material there is between the ground and the bedrock is referred to as overburden. And then when you get down to the bedrock, it's a solid rock. It could be sedimentary, it could be igneous, it could be all different kinds depending upon the location and the geology. Now, what happens when you have a reservoir behind an embankment, there will be seepage through that embankment, and all dams leak. The key is to control that seepage. And what we're very much interested in is how is that seepage occurring, and is it controlled, and where is the phreatic line within the embankment? Now, that's probably the most technical term we're going to use today, and let me just explain that. The phreatic line that we have here is the zone of the embankment that's completely saturated. And that's important to know where that is, because that will determine where the seepage comes from. In this case, the phreatic line is very high and it daylights on the downstream slope of the dam, so that if you were to inspect this dam, you would see that this lower part, where the red arrow is showing, would be wet, and there could be seepage observed coming from that. So that's very important to know and to control that. So there could be seepage through the homogeneous earth embankment fill. There could be seepage through the overburden, and there can be seepage through the bedrock. So as engineers learned more and more about dams, they saw how important it is to control the seepage through the embankment, so they begin adding features. And here we have a blanket drain, which can be a sandy material or a combination of sand and gravel, and it's designed to intercept any seepage in the embankment and make sure that that phreatic line doesn't daylight on the downstream slope, so you wouldn't see any seepage there. And that can be very important in controlling the seepage and making the downstream slope stable. Other things that engineers began to do, especially when they had problems with the overburden material, where there could be horizontal layers of more pervious material like gravel or sand, and that can develop some really high exit gradients at the toe, where water will want to well up at the toe of the dam. And in that case, they could install relief wells, and that helps to relieve the pressure at the toe so that the seepage at the toe is controlled. Other things that were done was to put in an upstream blanket. In other words, to extend the impervious material further upstream into the reservoir to make the seepage path much longer. And that was can be an effective way of controlling seepage. Then, if the overburden wasn't too deep, another effective way of controlling seepage through the overburden was to excavate a cutoff trench and then to place compacted earth material in there to make that zone more impervious, more watertight, and control the seepage through the overburden. And to control the seepage through the bedrock, they could excavate a trench and make like a concrete cutoff wall. Or the more common practice is to grout the foundation by drilling holes into the rock and then pressure injecting grout. In some cases, it can be a single line grout curtain. In other cases, it can be 3 lines, depending upon how much verification and water tightness you're trying to accomplish. And then as time went on and the construction equipment became more sophisticated and we're able to sort through available materials and make better use of them, engineers began to design zoned earth embankment dams. And here, making good use of the more impervious material, often clay and called impervious fill, putting that in the core of the dam and right through the cutoff trench, and then using the more gravelly and pervious materials on the upstream and the downstream parts of the dam. And that is a much better use of material, and you get a better performing dam. And then starting in the late 1970s and early 1980s, it became standard practice or very common practice to install a chimney filter drain and blanket drain, a much more elaborate drainage system within the zones of an earth embankment dam. And if you were to design a dam today, this is pretty much standard practice. And it provides a much more reliable and lower risk dam, so that if there was a crack to develop or a seepage path or something like that, it would be intercepted by this chimney filter and drain, and safely filter the water so that there's no loss of embankment material, and it would convey that water safely to the drainage system. These chimney filters and drains normally consist of a concrete wash sand or a carefully graded material that's compatible both with the clay core and the other zones of the embankment. And it generally, if there was a crack or a defect, it's very forgiving and it can heal that part of the dam. And then there are other features. If it's a very tall dam, we can have a toe berm or protect the upstream slope with riprap or other material to prevent erosion. The other common type of dam is a concrete dam, and that makes up another 7%. And that can be that slab and buttress type that we looked at. It can be a concrete gravity dam. It can be a masonry dam, a multiple arch dam, or a more modern type of concrete is roller compacted concrete. When you look at a concrete dam, we have a lot of the same nomenclature. A couple things are different. Here we have the left and right abutment like we would have for an earth embankment dam. And then in this case we have the overflow section of the dam. So there's generally a part of the dam that's the spillway, and that's designed to be overflowed. And at the toe of the spillway, there's normally a stilling basin to dissipate the energy that goes over that spillway. And then there's the non-overflow section, the part that's designed not to be overtopped. And then the part of the non-overflow section that's above the crest of the spillway is the chimney section. Here's a good example of a big concrete dam under construction, and you can see a cross-section of the dam here. And that in this case is a concrete gravity dam. It's solid concrete, and most concrete dams are built on a rock foundation. They're not built on overburden because they have a very small footprint, often less than a third of what would be the footprint required for an earth embankment dam. And that's, you can have very high flow gradients underneath, and that's why it has to be on a rock foundation. Now let's quickly look at spillway types. And there's a large